Next is Dhrubaditya Mitra from NORDITA. He'll tell us about the subtle intermittency of elastic turbulence.
Thanks, Sriram.
Still 12 seconds, sorry.
Is there power somewhere here?
Yeah. This is it. Yeah, if you have a USB-C socket. Do you have HDMI?
How do I put it?
HDMI.
Yes, I do. Okay.
What do you have?
I can convert it to HDMI. There was an HDMI.
Yeah, but where's it gone? I don't see it. Yes. Well, he's got. Should work. Oh, it's here.
Should be on that, yeah. Don't worry. Do you need a pointer at all?
Yeah.
Yes. But I also can do with power.
Should be some power.
No, that was, it doesn't matter.
Well, yeah, we'll want to.
It's okay. I will not stand between people and their coffee.
It'll be people and their photo sessions.
No, it's not.
Yeah, there you are.
Okay. It's not the one I wanted.
It's not the talk, yeah.
Okay.
You sure it's the right talk?
Yes, it is the right talk. Why? Oh, that doesn't matter so much. That just changes from one place to another. Anyhow, so I gave almost the same talk some time back, but I suspect there is almost no common audience here. So thanks very much. So that's my name. People call me by different names. I don't care. So fine. So I will talk about subtle intermittency of elastic turbulence. I will tell you in a moment what that is about. But before I do all that, I just want to start by talking about what is the turbulence problem. So this, as I understand, is a mixture of active matter community, statistical physicists, some turbulence people. So if I'm going too slow, if things are too boring, let me know. Okay, so there are many turbulence problems. There are mathematicians' turbulence problems, there are engineers' turbulence problems, there are physicists' turbulence problems. This is what I would call a physicist turbulence problem. It shows up in the simplest case where you have homogeneous and isotropic turbulence. And you want to know the statistics of velocity fluctuations. It's as simple as that. And the way you calculate that, you take the velocity difference across a length scale, you take it to the power p, you average it over turbulence. So this is like your pth order moment. And you ask, how does this scale with the distance? And of course, because it's a velocity difference, it can be both longitudinal or transverse. Now, if you look at only the longitudinal one, these are the blue ones here, and say that what are the exponents here? The exponents are typically called zeta p, and you plot them as a function of p, you see something that is not a straight line, okay? You see that the zeta p versus p is different from what Kolmogorov said, which is p by 3, and this is the problem of turbulence. If you start with the Navier-Stokes equation with reasonable assumptions of how you are studying it and can derive this zeta p versus p curve, you have solved turbulence. Okay, that will not get you $1 million, but probably get you a lot more. And the difference of these zeta p's from p by 3 is what is often called delta p, and that's what you could call the intermittency correction. These are the largest numerical simulation at the moment. Okay, so these exponents are also supposed to be universal. This is a phenomena called intermittency or multifractality. For a particular model, which is called the Kragner model of passive scalar, this program has been implemented reasonably successfully, for which we have a theory of the zeta p's. Okay, that's just background. Now, there is, of course, turbulence, and there is, of course, messy turbulence. Turbulence with bubbles, turbulence with dust, and the most interesting one, I believe, is turbulence with polymer additive. So this goes back to Tom's experiment. There is also a beautiful introduction to this in Daryan's Nobel lecture. And the idea is that you have a pipe flow or a channel flow or whatever in very high turbulence. And then you have added few parts per million polymers in it. There are very nice demonstrations of this you can find videos in the YouTube. So for example, if there is a fire hose that was reaching the second story, now goes to the fourth one with the same pressure head on it. So there is a huge drag reduction with few parts per million polymers. And at the same time, as you know, a laminar flow typically has a lower drag than a polymer flow, than a turbulent flow. But this is not relaminarization, because you can see an example here. So what is being plotted is the pressure fluctuations. You can see once you add the polymers, the drag goes down, but the drag is still a fluctuating quantity. So this is not relaminarization. This is drag reduction in the turbulent state. This is a very interesting problem and a puzzle. Some pieces of it are there, some pieces are not there. But that's the background from which what I want to talk about is a homogeneous isotropic turbulence with polymers inside it. So homogeneous isotropic turbulence has been often called HIT, don't add statistical to it. And then if you add polymers, you get P-hit. So then you can ask the question how turbulence changes the polymers. For example, the turbulence can do coil stretch transition to the polymers. Or for example, how does the stretch polymers changes turbulence? So in addition to Reynolds number, you will now look at, for example, the Deborah number, or you could define a Weisenberg number. But typically, it is some time scale of the polymer. Okay, so a polymer, of course, also has many different time scales, but you can think the time scale, the largest time scale is the polymer of relaxation is what I am calling tau p. And the flow also has many different time scales. So here also you choose the largest kind of flow time scale, the large eddy turnover time. If you took, for example, the scale of the time at the dissipation scale, then you could call it Weisenberg number. Both the conventions are used. I will stick to the Deborah number. So one way to do this, of course, is experiment, but experiments in polymers are particularly difficult. They break and things like that, but that you can ask experimental people. What we are doing is numerical simulation. What I am going to tell you, most of this talk is going to be about numerical simulation, which we believe are internally consistent, but it poses interesting questions. There are many known unknowns. So when we are solving this, the flow is described by the velocity u. The polymers are typically represented by the tensor C alpha beta. So you can say the end-to-end polymer distance is the vector r. You take a direct product of the vector with itself and then average it over the thermal state. You get C alpha beta. You can write an equation like this. It's not, the details of the equation, there can be discussions about that, but I am avoiding that at the moment. The important thing is that there is a time scale over which the polymer relaxes. That's the tau p. That's only one time scale. We are in homogeneous and isotropic case, and energy injection is by a Beltrami function that is limited only to the large scales. This is usual. This is quite common in turbulence research. So going back to going to long time back to Prasad's PhD thesis, is somewhere there. So there are many interesting things that can happen in a polymeric flow. One of the things is, for example, dissipation reduction. So you can say that I have a simulation, I'm looking at the energy dissipation rate of the kinetic energy, and when I add polymer, the dissipation range falls. This you can look at, we looked at that. But one of the things we tried to look at also was the spectra of the kinetic energy. And when you added polymer to the spectra of the kinetic energy, funny things happened at large Fourier modes. We didn't have then the resolution to really look at what was happening here. Now we do, and a lot of interesting things comes out of that part. So what happens from that part? These are our latest simulations. Also, there are experimental work a couple of years before ours. And the idea is the following. So you calculate the energy spectra, the kinetic energy spectra, And now you plot what is called the compensated spectra. So let me just remind you, if you believe in Kolmogorov, then the energy spectra should be k to the minus 5/3. If you remember, well, of course you don't, the intermittency plot that I showed you, the correction to the 5/3 is very small. So for the moment, don't worry about that, okay? And then you take the spectra, you multiply it by k to the 5/3, then you should get a horizontal line. So here we are plotting the spectra for different Deborah number multiplied by the k to the 5/3. So if it is Kolmogorov, you should get a horizontal line. So here is the case where the Deborah number is very low. You can think that the effect of the polymers are very small. As the effect at the Deborah number increases, the range over which Kolmogorov holds actually decreases. At Deborah number of 1, that's the smallest, then it starts increasing again. So there is a non-monotonic behavior in the part where the inertial range presumably is. Now what happens to the higher case? In the higher case, if you multiply by a different exponent, which is k to the 2.3, then, well, over here there is almost no scaling range, but you see the scaling range starts increasing. At Deborah number 1, the scaling range is almost a decade. It decreases and it decreases further. Yes?
So can you give us, please, more details? What is the ratio of the solvent viscosity to the total, and what are the values of the Deborah number?
What of the Deborah number?
So there are two
So
that
this
you specify the viscosity ratio and
yes.
the Deborah number.
So the viscosity ratio was fixed in the simulation, and in this it's not very easy to relate the simulation viscosity ratio to experimental one.
What are you fixing?
I don't remember it at the moment. I can tell you later. But the Deborah number here is 0.1. I'm sorry, here it's 1. And this went from something like 0.1 to something like 3. Okay. Yes?
Just going back to the equations, is there any reason for taking that form of the equations? Because for some reason it's actually not rotation symmetric. The conformation tensor equation is not symmetric under rotations.
In what way? Don't worry, everything is okay in that.
Yeah. It's just number convective derivative.
Don't worry.
It's a specific.
Don't worry about
upper
that.
convected or something.
It's
It's got both. Yeah.
If there is something wrong in the slide, that's a misprint. Don't worry. Okay. Yes.
The property of the viscosity ratio is such that the concentration is around 100 ppm.
Okay, so that's
No, but I mean, no, please, what is the numerical parameter?
Yeah, I'll tell you. The numerical value is around point. So if viscosity is around 10 raised to -2 or something, and it's the order of
we can talk about it after the talk.
Yes, I mean, all these relations are incredibly sensitive to that ratio.
Absolutely right. Absolutely right. Yes.
Can you sort of just give us an idea of the amount of dynamic range you have between the Kolmogorov scale, what I might call the scale for the Zinn time being, with the polymer to be activated and the energy containing region?
Right. So that is essentially the ratio of time scales.
Right.
So the
But
ratio.
that translates into a spatial scale, right?
So that you can, but here we mostly like to think about time scales, because you think the time scale of which ADs match with the time scale of the polymer, and they are I'm talking very qualitatively now, and they are the one which is supposed to stretch the polymers.
Sure.
So you can translate you can think of the Kolmogorov range as a range of time scales coming from the large AD turnover time to the dissipation time. And you can say where is the typical characteristic scale of the polymer relaxation. So when Deborah number is 1, that means the time scale of the largest ADs match the time scale of the polymers. And Weisenberg number would mean, so there will be a Reynolds number factor of 3/4 or something like that. Okay, so coming back, the usual way to analyze these things is through the fluxes. So you look at the fluxes in the Fourier space, and you say, look, the total energy injection must be the total energy dissipated. And in the steady state, the total energy injection has the following contribution: 1 from the nonlinear term of the flow, 1 from dissipation, 1 from the polymer, and final is the energy injection. So what we are doing is you go up to a maximum Fourier mode K and calculate the contribution of the flux and integrate up to that K. So once you plot that flux, so this is the most important quantity, of course, is the polymeric contribution of the flux. And if you plot that, you actually see something like this. Okay, so it goes up and remains kind of a constant. So the most elementary thing when you add something to a flow is an increase in viscosity. So the basic thing this should do is to increase viscosity and some more. So here, what I'm going to tell you next is a huge assumption. Okay. So what we are doing is we are taking the contribution of the polymer and breaking it up arbitrarily as two contributions. One which we call like a flux term and the one which we call a dissipation term. Now what is the dissipation according to the polymers? Again, complete hypothesis. This is the total energy dissipation in the polymeric mode divided by the total energy dissipation in the fluid mode multiplied by the contribution from the flow. Okay, so basically we make the polymeric dissipation look exactly like the flow dissipation multiplied by a factor. If you do that and subtract that out, whatever is left is this pi, which actually goes to 0 at high K, something which looks like the contribution from the nonlinear term. Now look at this. There are now, in this way of thinking about the problem, two fluxes. One flux, for example, here is because of the inertial term. Another flux of energy here is because of the polymeric term. If you are kind to me and squint your eyes properly and so on, you can imagine there is a small range over which this is a constant, and there is a small range over which this is a constant. Now, that's very difficult to see in a plot where you have both the fluxes. So when you keep pulling the Deborah number here and there, one of them becomes more of a constant than the other, but we don't have a simulation where both of them look like a descent constant. But that you also saw in my spectra plot, that there never was the case where we had two clean scalings of one decade in either of the cases. We have a clean scaling in one or the other. But if you are kind and look at it that way, you can imagine that there are two different fluxes in the problem. So if one flux is constant, then the usual Kolmogorov argument, which is just a scaling argument, gives you a k to the minus 5/3. If you apply a similar one here, you can no longer get a scaling exponent because now these contributions are connected to the polymeric degrees of freedom of the problem. All you can get is a relationship between how the energy in the polymeric mode behaves to how the energy in the kinetic mode behaves. So we don't have a theory of the number that is here, but we have a consistency check with what kind of spectra is satisfied by the polymers. That's one part of the problem. One part of the problem is telling you that there are two different scaling ranges. Let me remind you, the result is not only our own, there is also an experimental result from a Chinese and German collaboration. However, the following then happens, and this is the most interesting part. So you take the simulations or the experimental result, and you say, fine, I have Kolmogorov and elastic, but what if I look at the intermittency correction in each one of the two ranges? Okay, so you can take the structure functions, and you can see that, for example, S2 at large length scale has one scaling, at small length scale has another scaling. Okay, so from there you can calculate the exponents of the structure functions. You can say one of them is this and the other one is that. Okay, so one of them, for example, in the inertial range is just like usual homogeneous isotropic turbulence. It is close to p/3, which is this line, and then comes off. And the other one is something, I'm sorry, this one is the p/3 and the other one is something different. Okay, there you see again a departure. There is intermittency correction, but this is an intermittency correction about a different line. Okay, the strangest part is, to the best accuracy that we can determine, the intermittency corrections are the same in both of these cases. That's, I find, or we found, really weird. You have two different scaling exponents from the second order structure function, and each of the structure functions are different, but the departure from the usual normal scaling theory is same in both of these ranges. How do
Sorry,
you?
Dhruv,
Yes.
the 0.7n is something just by taking the first few points on the left and fitting the line to them.
No,
where does it come from?
it's basically from the second order structure function data,
From the second order.
which I basically k to the minus 3.2 that I showed you in the previous slide. And now you may ask why the second and not the third. So there may be the numbers, but that will only make a very small change to the story. Okay, so before I'm going to tell you how we are thinking about it. And the idea is the following, but before I go into detail, let me remind you a little bit how usual intermittency is thought about. So you have a flux through the scaling range. If the flux is a constant, then you will get Kolmogorov. And it's the fluctuations of the flux that tells you about departure from the Kolmogorov. Now this is the energy flux, and the energy flux, of course, is determined by the energy that is dissipated. So the structure function intermittency is inherently connected to a different intermittency that appears in the energy dissipation rate. The usual story is the following. You calculate the energy dissipation rate over a ball of radius r, you take it to the power q and do an average and look at how this scales with r, you get a set of exponents lambda q. Okay? The Legendre transform of these exponents are what gives you the F alpha spectrum of the turbulence, which is also called the multifractal spectrum. And this is the same multifractal spectrum that is related to the structure functions. That's how the two different intermittencies, one in the inertial range and one in the fluctuating dissipation, are connected to each other. Now, in this case, it's something very weird. The energy is being dissipated both by the polymers and the flow. Now, if you look at the energy dissipation, the probability distribution of energy dissipation in the polymer, you found that that's actually quite close to Gaussian. So all the large fluctuations of the energy dissipation are actually still coming only from the flow. So you calculate exactly the same, you play exactly the same game, but only with the energy dissipation rate in the fluid mode. And then you calculate the F alpha spectrum, which is our red line and the black line for two different Deborah numbers. They agree with each other. On top of that, I have data from homogeneous isotropic turbulence experiments. And you see that both of them agree with each other reasonably well. So the clue to the problem is that the value of the flux itself sets your exponent, but your intermittency connections to the exponents are set by fluctuations of the flux. And the fluctuations of the flux are completely determined by the fluctuations in the flow, not in the polymeric mode. That's as far as we understand it. But to summarize this part, I'm not done yet. The kinetic energy spectra has two ranges. One is inertial, one is elastic. The inertial range is Kolmogorov-like, and there is no theory for the elastic range exponent at the moment. So that's the first problem. Both the ranges have the same intermittency correction, and the intermittency is same as the usual Navier-Stokes intermittency. So the good thing about the second part is I haven't given you a second problem. You just have the usual Navier-Stokes intermittency problem, which you always had. Okay, so far so good. So now let's kind of look at the problem in a slightly broader phase space. We have the Reynolds number in one axis, and we have the Deborah number in the another axis. So if we are in small Reynolds number and say 0 Deborah number, then typically we have laminar flows. We increase the Reynolds number, the flow goes through various instabilities, we get into turbulence, we get Kolmogorov. Now there is also a whole elastic thing, a whole interesting phenomena happens. If you keep your Reynolds number low and start increasing your Deborah number, that's the part I will come to, and this is the part I already talked about. So if you are in large Reynolds number already, you increase your Deborah number, your energy spectrum breaks up into two ranges. You go up further, it is again back to Kolmogorov-like. Okay, that's the part I have already told about. Now I am coming to this part. The Reynolds number is small, the Deborah number is increasing. So this started, the most interesting things of this started coming around 2000 from Victor Steinberg's lab. There were also other earlier work by Shakfei and so on. These slides are not well referenced. The references are in the paper. Don't blame me on that. So the idea is that there is a laminar flow which can become unstable due to elastic nonlinearities from the polymeric degrees of freedom. For a large Deborah number, the flow can be actually turbulent. Now, turbulent in what sense? One is it has a power law spectrum of energy. It is mixing, but it is smooth. Okay, so there is no theory for the exponent of the energy spectrum except certain inequalities and various attempts I am not going to get at. But interestingly, this is the energy spectrum, but these results are from Victor's paper quite some time back when he was calculating the energy spectrum by measuring the energy in time at one point in the flow. And from that, what he gets is an exponent of f to the minus frequency to the minus 3.5 over not a very large range. Okay, so this is now our simulations. So we have taken as far a big box as we could do. The concentrations of the polymers are fixed, and I'm slowly increasing the Deborah number. If the Deborah number is very small, or polymers are not at all there, then this is a flow that has no turbulence in it. Okay, so you can see that there is no energy spectrum. It's just falls off exponentially, and that's the Newtonian one. Now, as I start increasing the Deborah number up to, for example, to something as large as Deborah number of 9, there is a nice k to the minus 4 scaling range that develops, which is what we are calling elastic turbulence. And there are various checks we have done. For example, we take the same equation and we remove the advective nonlinearity. We still get k to the minus 4. We have changed the model of the polymers. So we have changed model of the polymers from Phe to Oldroyd B to Phe P. In one case, the polymer can extend as much as it wants. That's the Oldroyd B. The Phe P, the polymer has a maximum length, and we still get the same thing. We have tried different forcings. We have tried different range of simulations. It's reasonably all k to the minus 4. Okay. At the same time, you can calculate the energy spectrum in the polymeric degrees of freedom. The scaling there is smaller, but it's looks closer to k to the minus 3/2. You can connect these two by a scaling theory, and you can get something like if one is 4, the other will be 3/2. These two are consistent. Still no theory, remember? Theory of any one of them will give you the other. Okay, that's the background to elastic turbulence. This is just telling you that in our simulations, we capture elastic turbulence in a reasonable way. And
So just remind me, the forcing is done how?
Very large scale.
Okay, so it's some.
It's first few Fourier modes.
Do you see any hint of waves in the elastic turbulence? The 3/2, of course,
Yes, so
the
that's-
tip-off on that.
That's of course is a very important question. No, but that may be limitations. I don't think we rule out waves yet, but at the moment the way we are thinking about this problem doesn't include waves. So for example, if you use the thing that these are actually like Alfvén waves,
Exactly.
if you do that, you can also get a correspondence between these two exponents. That doesn't match.
Yes, but you do not have the second time derivative to get the Alfvén waves here. And your Reynolds number is so minute that effectively it's one-time derivative and you can't.
I agree with you. So that's why I think the elastic turbulence is not coming from Alfvén waves. Okay, so what we did, for example, now we again see what turbulence people do is they look at the complicated equations and they say, look, there's not much you can do about it, but then what is large and what is small? And in an extremely fluctuating situation, what is large and what is small is not always very easy to determine. So you look at the contributions of the terms to the energy flux and say what is large and what is small. So here what we find is that the contribution to the flux of the nonlinear term is practically 0. The polymeric term and the dissipative terms are the ones that are comparable to each other. So if you kind of write a balance between the two, then you will get a connection between the polymeric degrees of freedom and the kinetic energy spectrum, which gives you xi is twice chi minus 1. This is a simple scaling theory, nothing special about this. You can do it in your sleep. And this actually holds in our simulations. So let me just kind of try to remind you where we are. So now we are talking, I just talked about Fourier space behavior. I want to now talk about real space scaling in elastic turbulence. So what happens in normal turbulence? In normal turbulence, if you look at the second order structure function, and you say, of course, I have a finite viscosity, so my flow, whatever the velocity as a function of space is, it must be Taylor expandable. So at very short distances, it must go as r square. And at somewhat larger distances, it goes as r to the power zeta 2, which is the non-trivial exponent. And there is a scale when one transits to the other, which is the Kolmogorov scale. Okay, that's standard. And this zeta 2 is 2 by 3. Now, what does one expect in elastic turbulence? See, there is no Kolmogorov scale to play with here. We cannot tune, I mean, this whole thing is happening where viscosity is important. There is nothing to tune except only the Deborah number. Okay? So, as at small r, we find that the structure function goes as r squared. But if there is a different non-trivial exponent, there must be some other scale that must appear. Okay? So let me show you some data. So on the left, this is from a very nice paper of Schumacher, Srinivasan, and Yakut. What they do is they take the structure function and they divide it by r to the power twice n. So if this is just the small r behavior, the plots are going to be horizontal. So as you see at small r, they all become horizontal, which basically means the functions are Taylor expandable, not a big deal. And they depart from that as you go to larger r. If you look at our data, and of course, where they depart, which is not in this plot, depends on what your Reynolds number is. If your Reynolds number is small, then they will keep this straight line for a long distance. If it is not, then it will be cut off at a small distance. Now, if you look at our data, this is the structure function divided by r square. It is horizontal at small r, but when I change the Deborah number, the transition scale almost doesn't change. Okay, there is something happening here, some different scaling possibly, but I can't really see what that is. Okay, so is there a non-trivial scaling that we can detect from these structure functions? Okay, so it shows trivial scaling at small r, which is just what I have told you now. Now the non-trivial scaling so far is not revealed. But remember, the energy spectrum go as k to the minus xi. So simple power counting will tell you that the structure function should go as r cube. Now r cube is of course subdominant to r square. So that's why you don't see it, right? So whatever is non-trivial is hiding in the subdominant term. That's the devilish nature of the problem. So the idea now is that what if we define a different kind of velocity difference? So we define a velocity difference where instead of looking at velocity difference across r, we take r and minus r. So that's by construction, the linear dependence is subtracted out. Okay? So if we look at this different kind of velocity differences and then calculate their structure functions, interesting things start happening. So here I am plotting this velocity difference and the square of that. So this is the analog of second order structure function, but now with a slightly different kind of velocity difference. See, the velocities have the same nature. Just taking a different velocity difference doesn't change their nature. The whole purpose of this is to take away the dominant term so that we can look at the subdominant term. And you see a reasonably clean scaling of r cube, which is exactly what was expected from the energy spectrum. So that means if you think that the velocity has one scaling exponent, for example, this one has a subdominant expansion, then that number will be 3/2. So if you look, for example, that, okay, I look at velocity difference across a length scale, there is a dominant term which goes as r, and there is a subdominant term which goes as r to the power h, then h would have the exponents of 3/2. Okay? But now let's look at the higher order ones. Once we do the higher order ones, these are different exponents, and now these are the higher order exponents being calculated, but from this very different, not very different, but somewhat different velocity difference. Okay? And you see each of the cases, actually you get a different scaling exponent. You take this new set of zeta p's and plot them as a function of p, you get a completely different behavior. So they are different from 3p/2, there are intermittency corrections. And these intermittency corrections and all the exponents are very different from the p/3. when we change the Deborah number, which essentially get the same ones. So the conclusion at that point is that elastic turbulence also has intermittency, but this is a very different intermittency. It's smooth, so the intermittency manifests itself in the subleading term, which you can now try to imagine that if you're trying to do a theory of that, it's going to be very, very difficult. Yes, please.
Sorry, I'm slightly confused by what the left-hand side plot implies. There is a point on all of these curves where you go from one behavior to another.
Yes.
Which defines a typical length scale.
Yes.
What is this length scale dimension here? Because your equations of motion do not have a length scale in them.
Yes.
So what is that? Is it a portion of the system size?
That's a very good question. Honestly, I don't know. We also said in our paper we don't know. But I would think that this is related to the smallest scales where my resolution is. And if I go to higher and higher resolution, this scale will go lower. Because I can't think there is another scale where there is a cutoff. I mean, there's nothing else, as you said. Nothing else to make a length scale. So I don't know. But fair enough. Okay, so now I have this new set of exponents. And how are those exponents connected to other measures of intermittency in the problem? So if I look at, for example, the probability distribution of velocities, and here again it is the velocity difference, which is the new kind of velocity difference. And you see that this dashed line is the Gaussian. These tails are definitely far away from Gaussian. So that's the second evidence of intermittency. The third evidence of intermittency is the kurtosis. You can calculate the fourth moment divided by the second moment. And we know that it scales in a certain way in Navier-Stokes turbulence. Here it scales much more worse in the sense that this is much more intermittent than usual Navier-Stokes turbulence. This is not the same intermittency. Now, if you now try to do dissipation range intermittency, if you now look at the fluctuations of dissipation, this time, again, the dissipation in the polymeric mode are quite close to Gaussian, so they don't have intermittent behavior. But the one that are close to the one that in the fluid are actually, they do show intermittent behavior. But if you now calculate the F alpha spectrum, the multifractal spectrum of turbulence, you find that that's not actually very similar to what you have found in homogeneous isotropic turbulence. There are some agreement, but not completely. So, and these exponents, these corrections, we believe, are different from usual Navier-Stokes turbulence. And they have appeared in a weird way, in the sense that they have appeared in corrections to subleading terms. And that's what they are. So finally, well, I'm 10 minutes or 12 minutes early. I should have spoken slower. Never mind.
We have time for questions.
Yes. So if I think of polymeric homogeneous isotropic turbulence, it can have two scaling ranges, one inertial and one elastic, but they're both with the same intermittency correction. There is a non-trivial scaling in elastic turbulence that is revealed by the second difference of velocity, not the velocity difference. It is intermittent, that is evidence from structure functions, probability distribution functions, kurtosis. The dissipation of kinetic energy is also intermittent, but the Kramer function is actually different from homogeneous isotropic turbulence. So what are the open problems? First, a theory of energy spectrum in elastic turbulence. That I think is long overdue. Second, a theory, if we can say, of intermittent corrections in elastic turbulence. But I suspect if we have a theory in elastic turbulence, we may also be able to understand the elastic range that we found in the more turbulent simulations that we ran. Possibly similar ideas will work because there is a similar flux balance. In both of these cases, it is the polymeric term which balances the dissipative terms. And then there should be a theory of intermittency of elastic turbulence, and there is a much lower hanging fruit, which is the connection between dissipation of kinetic energy in elastic turbulence to the structure functions in elastic turbulence. That's a multifractal problem that we still haven't finished working on. Okay, so, who wants to know about publication? So this is done, part of the work goes back to Rahul. The first things I told you was Rahul, me and Prasad. And then some of this is, and rest of them are Prasad, me and Marco, who is at Waste, and Marco's postdoc Rahul Singh, and that's their whole group. And that's the end. Thank you. Yes, please.
Yes, thank you. I have more a comment rather than a question on the assumption that you've made to separate the fluxes. So maybe if you could go back to your slide.
Yes.
Yes. So here you're making a big assumption to separate out different contributions, and I don't think that this assumption is necessary. You can make this very precise by redefining the way that you calculate your fluxes. Rather than doing it in Fourier space, you take a subgroup-scale tensor, and you can have a direct correspondence between your Fourier space definition and that definition.
Okay.
When you do that, you can cleanly separate out what would be going between the equations, let's say, which is what the term that eventually becomes constant on your left-hand slide because that has the much dissipation, and what is conservative, so what goes to 0 is k going to infinity. You can cleanly separate that out.
I think this, we should sit down together and have a look. Thanks very much.
Yeah.
If it can, that will be great.
Yeah.
Rahul.
To the extent that the resolution will always be a challenge, you did not think of trying this in 2D. One of your co-authors has a 16384 squared simulation.
Because the 2D turbulence will have other problems, right? They will, I mean...
What cascade?
You mean the entropy cascade?
Yes, anyway, we can discuss it
That-
later.
No, not in 2D. I mean, the same spectra were found in Kolmogorov flows in 2D by Rebecca Benzin and colleagues. That's, I mean, this is a good suggestion. There seem to be exactly the same spectrum there.
And then you are, in the Kolmogorov flow, you are forcing at large scales.
Yeah.
Right, so that basically you're getting an entropy cascade down to the scales.
Well, I mean,
That's fine.
It's zero inertia. I mean,
Yeah, you're not in.
No, what I think.
No, but this is not zero inertia. This is the large inertia simulation.
So when
oh, you're talking about.
Yes, yes, yes. Yes, please.
Yeah, go ahead. Please.
So,
Anyone?
No, he was first.
So for your T to the -4 spectrum in elastic turbulence,
Yes.
what do you expect for the coefficient so entropy cascade or energy cascade itself doesn't
No, I don't like to think of it even as a cascade. Because you see, dissipation is valid at every scale there.
Yeah.
So I don't want to think of it even as a cascade.
Yeah.
But then I don't know what to think. I don't know what, I know what not to do. Mike?
Yeah, well, you've almost answered my point. I mean, this is, cascade language seems to be inappropriate. For
Yes, I think so too. Yes.
Because basically the nonlinearity is just scattering energy from every wave vector directly into every other wave vector, rather than kind of neatly flowing through Fourier space. So I do think it is a bit of a false friend to be thinking too closely of Navier-Stokes turbulence.
I think so too. And then Prasad was trying to convince me yesterday that we should think of it non-locally, which is similar to what the direction you are thinking. Yes.
Can you or someone remind me what the spectrum is, the energy spectrum, for the sort of turbulence, that which is called turbulence in the swimming of concentrated bacterial suspensions at very low runtime? There must be a spectrum that somebody's measured for that, and
Yes.
I don't know what it is.
You would know, right?
Well, I mean, I can do full transparency on this yesterday. So the spectra in microswimmers and the spectra in elastic turbulence are very close to each
Yes.
other, -4, and that's why I was kind of calling this an upper convective turbulence more than anything, because that's the shared ingredient there.
If you also look at, for example, turbulence with bubbles, what is called pseudo-turbulence, you can also get -4. So there is possibly something common hiding there. Yes.
Rahul had a comment, and then
The comment is that if you look at models for bacterial turbulence, you do get so-called inertial ranges with different powers, and the value of that power can be model dependent, parameter dependent. In one case, if you push some parameter very far, there seems to be something universal, but I think we still need lots more exploration before we can give a good canonical answer.
Mike.
So just to clarify, the -4 is the energy, right?
Yes.
So
Yes.
the velocity is that -2.
Correct.
So -2 for the velocity has a kind of ultra universal explanation, which is that there's a finite correlation length of a random stress field.
Right.
So
Which you also get in stability composition.
correct. So well, I mean,
Interesting.
Ricardo is the one who said this first, essentially. So at large scales, this seem to be just a collection of random dipoles, or to be precise, the leading singularity. And because these are dipoles as well, I think this is the universality. At small scales, it seems to be in 2D at least. It's much closer to the Suffman.
So when we did big numerics on Model H, spinova decomposition, we were a bit puzzled to see this k-2 in the velocity autocorrelation function, but it's the same thing. Basically, you have a finite correlation length for where the interface is, and this is just putting stresses of random signs all over the place, and you get that k-2 count.
Just to point out, k-2 was Mike Graham in 2008.
Yes, with Hernandez.
One comment, sorry, if I might, on that problem. These studies presumably are not Stokesian, what he's doing. At least unsteadiness exists.
Unsteadiness exists,
So in
yes.
principle, the k to the -2 should be cut off on a scale given by the unsteadiness, right? There should be a finite, on a scale given...
Well, this is an astronomical scale.
Sorry?
It's a very...
Even for microbial suspensions, it's not astronomical. It's a millimeter.
Well, millimeters, yes.
Experiments on centimeter scales with
Yeah.
But kind of to relate to Mark's previous comment, so in microswimmer suspensions there was a work by several groups, but I think the first was Giuseppe Ganella, where they showed that there is no cascade, and that the fact that you see a power law does not mean that there is a transfer of energy from scale to scale. The analogy of seeing similar spectra in elastic turbulence really suggests that there might be a similar mechanism there.
Anybody else? I am around.
On that note, let's thank Dhruva once again. And